Okay, we are going to start on three-phase Y systems now. So this is part one of three-phase Y systems, and we're primarily going to be talking about three-phase Y voltages and how we come up with, I'm sure you've heard of it, root 3. So when we're looking at the three voltages generated off of a generator, we're going to refer to them as V, N to A, N to B, N to C. So that direction in that moment of time. So what does that really mean? That means that we have there's our little a, little b, little c, E, N to A. So N is the star point here, right here. And so voltage, and that's what star point is, where N towards A, and then what would occur next 120 degrees later is N towards B, and then voltage N towards C. So the three ways that it would be generated. Now looking at the wiring diagram for the three Y connected coils, once again I talked about we're going to use big A and little a, big B, big C, and little c. And so if I was connecting up this generator, so it's important that the polarity is correct. So we would connect our three lines up to go to our load, A, B, and C, to big A, big B, big C. And the other end of it, we'd make sure that the three generator coils were connected up in Y. So we would put little a, little b, and little c all together. And then that would also be the point that we would ground. And that would be our neutral. And once again, neutral, responsible for carrying the unbalanced current and keeping our load voltages, our phase voltage, across each load at its required voltage. So a diagram of a three-phase Y connected, this is the load now that we would connect up to the generator. In this case, we have a Y connected load. We could have a delta connected load, but this is topic is about Y. So when we connect up the load, we would run line 1, so A, B, and C out, and they would connect up to the three loads. And you can see the three loads are star connected. This could be a motor that would show that it would be balanced. You don't need a neutral for a motor load. But if it were unbalanced or if were individual loads, we would always definitely need a neutral going back. So in this diagram itself, it's a three-phase Y connected load, a three-wire Y load, and we can have a three-phase four-wire load as well, and that's where we require a neutral. So the only thing I can think of, top of my head, that does not require a neutral would be a motor. Okay, so sine waves of the three voltages across the three loads. So we had the generator voltage, E N to A, E N to B, N to C. And now if we look at the other end, and we were to put our oscilloscope across the three loads, we would have a volt drop from A to N. And that would peak first, 120 degrees later, Vn to peak. So the load would drop across the second load in phase B. So Bn to peak. And then in the third load, which is in phase C to N, we would see the volt drop, peak 120 degrees later, and then we'd go back to A to N. So now we could draw out these sine waves every time to show these volt drops. Three-phase Y system, this is kind of the whole picture here. So on the left here is our generator, and on the right is our load. And in this case, we've got our generator connected up in Y. And as the magnetic field goes by, it will generate a voltage on from N to A, N to B, and N to C. And then we have a load connected up over here from A to N. So we'd have volt drop AN. And then the next thing would happen, we'd have a volt drop from B to N. So we'd have voltage BN. And then we'd have, third one is 120 degrees after B to N. We'd see voltage rise up, and we'd have volt drop VC to N right here. So supply, your phase voltage is EA to N. It generates 120 in this example. B to N is 120. C to N is 120 on all three of these coils. And we'd say the load phase voltage is VA to N 120. We'd see a volt drop across there with our meter of 120, and VB to N 120 volt, and VC to N 120. Now line voltages. So we have phase voltages. Okay, so this is a phase voltage, but then we have our line voltages. So we have VA to B or EA to B, So that'd be VAB, and then we have VB to C, and then we have voltage C back to A, so voltage CA. Okay, so this is where the 208 comes in when we're looking at line voltages. So this would be a 120 208 volt system, and so line voltage VAB, VBC, VC to A. So that brings us to rule number 1 for Y systems. Line voltage is going to be equal to phase voltage times 1.732, which is root 3. So if you take your calculator and you just put in root 3, square root of 3, let me just bring it up over here for a second. Square root 3, it comes to 1.732 is the number. So that's what root 3 is. Okay, so we could use this interchangeably, either 1.732 or square root of 3. So often we'll write it out like this. Sorry, V line equals V phase times root 3. And so if I knew the line voltage, I could solve for phase voltage. So V phase would be equal to V line divided by root 3. So we could go that interchangeably. Just need to know one of the values, either line voltage or phase voltage, and we can determine what the other one is. Okay, current flow in a Y system. All right, so if we look at current flow, so we have a Y connected generator here, and we have a Y connected load. So what does that look like? Well, we have our phase currents IA to N, IB to N, and IC to N. The line current, we would just call it line A, line B, line C, so it's IA, IB, and IC. So whatever is in the phase in the generator right here, that's the phase. So that'd be IAN, is the same value that's going to flow out on this conductor if we put an ammeter right there. Our ammeters are connected up in series. This would be line current IA, and then we call this phase current IAN right here through the phase and balance out at that star point, whatever we needed to. So the key thing here is rule number 2 for Y systems is that phase current and line current are the same value. They are the same. So I phase is equal to I line. All right. Now that may seem obvious because it's just one path for the current to go through. The phase current and line current are the same, but when we go to delta loads, this changes, and so does the voltages. So we have to make sure that we differentiate these rules, and these rules are quite important. So rule 1 was line voltage equals V phase times the square root of 3. Rule number 2 for Y is phase current is the same as line current. So instead of drawing that 4 quadrants in that method, you see we're often going to have use this circle showing our angles on it for our phasor diagrams. So let's just note which way. Remember, there's our origin right in the middle, and we always call the positive horizontal right here, we call that the reference line right here. So reference, and that is at 0 degrees. Same as we did in second period. If we had series circuits, we put our current on a reference. If we had parallel circuits, we put our voltage on a reference, and then we plotted currents from there. If we go up from the 0, we say that that is going in the leading direction, or it's ahead in time. So if I had a phasor at 0 degrees and another one at 30, the one at 30 would be leading the one at 0 by 30 degrees. If I plotted one down here, let's say at 330, somewhere here, I would say that that phasor is lagging my reference by 30 degrees. So it's at 330. So ahead in time, you would always add degrees. Behind in time, you would have to subtract the degrees from our reference. So let's put another one out here. Let's say it's at 210. If I were to draw something that was leading the 210, one at 210 right here, I would have to plot it up here, or add degrees, 240 let's say. If it was behind my vector here at 210, I'd have to say it's lagging it, so I'd have to subtract degrees to plot it out. Okay, so just a little bit about using this and which way is leading and lagging, which way is ahead in time, which way is behind in time. Now, there's our three. Here's our supply coming in here, and then we've drawn up a load here. So there's a load here in VA to N, B to N, and C to N, and we have our three-phase voltages: VA to N, VB to N, VC to N. We're going to plot these all out. So we're saying we're going to determine our line voltage, but first we're going to plot out where our phase voltages go. So our phase voltage, we always use VA to N as the reference. So if I say that I'm using something as a reference, I put it at 0 degrees. So I plot it right here. Now if I'm using positive phase rotation, I know VB to N will peak 120 degrees after VA to N, or it's behind it. So 120 degrees behind VA to N. That means that I have to plot it 120 degrees down. So subtract 120 degrees. So 0 is the same as 360. 360 minus 120 to go lagging gives us 240. So if I wanted to, so if I see that again here, VAN is right here, 120 degrees later is VB to N. If we put that on the diagram, VB to N is 120, and we would have to plot it on our phasor diagram back 120 degrees, so it would be at 240. And if we look at VC to N, we know that the next thing to peak 120 degrees after B to N is voltage C to N. So it's back 120 degrees from voltage B to N. So 240 minus 120 puts us at 120. So there's where we'd plot our three phase voltages on a phasor diagram. So they're 120 degrees apart, and then after VC to N, we'd be going back to V to N. So there's your 120 degrees back. We could say voltage VA to N lags voltage VC to N by 120, or we can say it leads voltage C to N. VA to N would lead voltage C to N by 240. So both are correct statements. Okay, what about line voltage? So let's go with that. So if I put a voltmeter from A point right there, and so there's my voltmeter, and I put the other end of the voltmeter here, we already know that V line is equal to V phase times root 3, or 1.732. So it should read, if this was 120 volt times root 3, it should be approximately 208. I think it's about 207.8 volts, something like that. Now, how do we come up with that? So that's what we're going to be working on here for this next portion on these line voltages. And we have to come up with a formula for this. And what we're going to do is we are going to walk the path that our voltmeter would see. So what do I mean by that? Is I'm going to write this out, VAB, a little bit differently. When I'm really saying what is voltage A to B, I'm saying what is voltage A to, so 2B. And what that means is I have to walk through what the voltmeter would see. So I have to say one lead goes to, let's say this is my voltmeter, to A, and it measures the difference potential from A to B. So in order for me to get from A to B through the load, I have to go from A to N, and then from N to B. So I have to add voltages up for AB. I have to add voltages A to N plus voltage N to B. And this is all at, where are they on our phasor diagram? So this is a sign for, that's a little bit of crazy vector there. Try that again. Vectorially. So we have to add those voltages up vectorially to see how to get voltage VA to B. So how do we show line-to-line values of voltage on a phasor diagram? VAB, VBC, VCDA? Well, that's what we're going to discover right now. How do we get this? Line voltage equals phase voltage times root 3. Okay, so as we said, line voltage VAB, we said we walk from A to the N and N to the B. So VAB is equal to VA to N plus voltage N to B at their angles. And we'll get line voltage VAB. So where's this N to B thing? Well, we have voltage VA to N. It's on our reference. It's right here. Okay. We have that one of our formula. And we have voltage B to N, but not voltage N to B. So what voltage N to B is exactly the opposite angle, same magnitude, exactly opposite angle of voltage BN. It's voltage NB. So what is opposite? That means it's 180 degrees from voltage BN. So where is that? Right there. So if I take 240 and I subtract 180, that leaves me with 60. I have to plot voltage NB at 60 degrees. Or I could add from 240, 180 gets you to the same place. But you have to remember, when we get to the 0, you're going to have to keep going in degrees. So you could do it either way, but I find it easier to subtract to get to the opposite on this one. Okay, you can add or subtract 180. You're going to get to the same point. Okay, so there's my two voltages that I need to add up. 120 volts at 60 degrees plus 120 volts at 0 degrees, or 360. So in order to do that, I can make a cosine sine chart. So this is one method. So I put the vectors that I need to add up, VA to N, which is 120 at 0 degrees, and break that down into its horizontal and vertical components. So in order to do that, I take, this is my hypotenuse, I times it by the cosine of 0 degrees, and I'll get its horizontal component. And in order to get the vertical component of this vector, I take 120 and I times it by the sine of 0 degrees. Well, sine, that is 0. So sine 0 times 120. For voltage B to N, or sorry, N to B is the other vector I needed to add up. 120 times the cosine of 60 is its horizontal component. And 120 times the sine of 60 is its vertical component. What's left for me to do is to add up the horizontals, get a total horizontal, then add the verticals, and get the total vertical. And then we'll plot them out. So 120 plus 60 is 180. And then the total vertical is 103.9. So if I plotted that out, total horizontal is 180. The vertical is 103.9. And then all I have to do is go from my origin to where we ended up, or I can use Pythagorean theorem to find the result. So 180 squared plus 103.9 squared, and square root that, we got 208 volts. Let's have a look on our phasor diagram. So 180 squared, so that's the horizontal here, and then the vertical, 103.9, and get our hypotenuse. It's roughly 208 volts. So that would be voltage A to N plus voltage N to B, which gives us our voltage VAB. Now what angle is that at? Well, we can determine that too. We have our horizontals 180, and our hypotenuse here on the triangle, or our line voltage, is 208. So if I have the adjacent side and the hypotenuse, I can use the cosine ratio. So cosine theta equals adjacent over hypotenuse. So I take 180 and I divide it by 208, and then second function cos that, and I get 30 degrees. So we see that this angle is going to be 30 degrees. Okay, so 30 degrees. Now we can say, I'm just going to erase this screen here for a sec. This isn't always. So when we add up the two voltages, that we require, voltage NB and A to N and voltage N to B that we require, we're always going to get our line voltage at 30 degrees ahead of VA to N. So this would be rule 3 for Y. Okay. So in Y system voltages, in a Y connection, V line always leads V phase by 30 degrees. Okay. So by that we can probably predict voltage B to C and voltage C to A, what their magnitude is. We're going to know by taking our phase voltage, multiplying by root 3, but we're also going to know where to plot them, 30 degrees ahead of their phase voltage. So 30 degrees ahead, that's an always. Okay. But what we're going to do right now is that's due to the position of the windings, 120 the electrical degrees between the phase voltages. When we add them up, it always ends up 30 degrees ahead. We're going to try the same thing though. We don't always have to do that cosine sine chart when we're adding things up, adding vectors. We can use our calculator to do the same thing. And so let's just pull up the calculator here. Okay. And let's try adding up our two phasors that we needed to add. We needed to add 120 at 0 degrees plus 120 at 60 degrees. So to do this on the calculator that you had, you have to put in the correct mode. So on yours it's mode 3, second function 8. Okay, this one this is a virtual calculator. It's a little bit different. Okay, but it's close. And you should see up in the top left-hand corner r, theta, and degrees. So now to do this, once you're in the correct mode, so remember mode 3, second function 8, we can just simply add up our vectors. So I'm going to start with the first one right here, which is VA to N, and it's 120 at 0 degrees. So I'm going to enter that in, 120 DMS, that's where it wants you to put the angle in now, 0. And then I'm going to hit add plus my next vector. 120 DMS, we're at 60 up here. We're at 60. So DMS 60. Oops, I hit DMS twice. I better delete that. There we go. 60 equals 207.846. So there's our value of voltage. That's what we determined already. So we just added up both those vectors. Now what about angle? Well, that's a great thing about this calculator. If you want to go and toggle and see what angle this is, you just hit second function exponent. It says 30-degree angle. And it doesn't have anything there. It doesn't have a negative. It has a positive. That without anything there, it means positive. So that means I go up 30 degrees and I plot it there. So where it's at 30 degrees. Okay. So that simplifies things a lot. Let's just run through that one more time while we're here. So 120 VA to N, DMS 0, plus 120 DMS 60 equals 207.8. There's your magnitude of your resultant vector, or line voltage VA to B. And to see the angle it's at, second function EXP, 30 degrees. If I want to go back, second function EXP. So I can toggle between the two. Okay, so that is a huge advantage for us. For us doing cosine and sine charts, the horizontal vertical charts, the entire time, we are going to be adding up tons of vectors. We're going to be adding up voltage vectors, current vectors to find our neutral. And we get to delta, we're going to be adding up phase currents to get our line current. So real big advantage and time saver, very accurate as well. So I suggest you learn how to use that system and know how to break it down if you had to with your cosine sine chart and add your vectors up that way. So just a little thing here, where did that root 3 come from? Okay, this little diagram, it is in your ILM. And here's your voltages that you need to add up. So you've got your VA to N here, which is 120 at 0 degrees. Here's your voltage N to B, which is 120, and we know it was at 60 degrees. Okay, so it's called a tip to tail method. So essentially, you just the tip of the first vector, okay, right here, we just move this over until the, sorry, that's the tail of this vector. That would be the tip, sorry, the tail of the next vector. So the tail is here, and then the tip of it is right there. So over and then up 60 degrees to there. And then we do a line all the way across. That's our resultant vector when we're adding these two lines. So that's our line voltage in that case, voltage VA to B. So if I take from this point here and I draw a straight line and make two right angle triangles out of this, and then I label this side here of the first triangle as 120 volts, okay, and the angle between these two lines is 30 degrees. Over here, voltage NB is right here. That is the hypotenuse on the second triangle. So that's the hypotenuse. And it also makes a 30-degree triangle with this adjacent line here. So if we look at what we're solving, we can solve for this portion right here by taking our hypotenuse. So that's a horizontal portion of this triangle, or adjacent side. So cosine theta is equal to the adjacent side over the hypotenuse. And if I want to solve for the adjacent side, I would take cosine theta, so which is 30 degrees in this case, times by our hypotenuse, which is in this small triangle here, right angle triangle, it's 120. So to figure out this half, cosine theta, so cosine 30 degrees times our hypotenuse, which is 120. Okay, I'm going to leave it at that. Okay, let's look at the second triangle here. Okay, so our hypotenuse is 120, and I want to figure out the side adjacent to the 30 degrees. Well, it's the same formula. The side adjacent here, or the second half of our length of our total line voltage, adjacent is equal to cosine of 30 times our hypotenuse, which is 120. Same formula. So essentially, to figure out the entire length of that, could go, so VAB would be equal to 2 times cosine of 30 degrees times 120. All right. So if I were to take this and figure out what 2 times cosine theta is, so 2 times cosine of 30 degrees is 0.866. It comes to 1.732, or we know that that is the same as square root of 3. So there's our V phase. That's how we get our formula. V line is equal to V phase times root 3. So through math, you can see where the root 3 comes up with. It's 2 times the cosine of 30. Okay, so how that works out. Let's see. So Y system voltage in a Y connection, V line, as a reminder, rule 3 there, always leads. V line always leads V phase by 30 degrees. Okay, so we did voltage A to B, and I showed you how to use the cosine sine charts, and then we went through and we did the adding up of the phase voltages at their angles with the calculator. So from this point on, I'm just going to use the calculator to figure out the other two line voltages. So our first line voltage was VA to B. Our next line voltage is going to be voltage B to C. So if we say that this is our voltmeter right here, it's connected up to B and to C, and I want to know what the voltage B to C is. I have to walk the path of that voltmeter. So it's going to be phase voltage V to the N, and then voltage N to the B. So VBC is equal to voltage B to N plus voltage N to C at their respective angles. Let's see what that would look like. So we've got voltage B to N here, which is the one we require. So let's remember the formula we just came up with. Voltage BC is equal to voltage B to N plus voltage N to C at their angles. So we've got voltage B to N. It's 120 volts at 240 degrees. So we got our first vector. Now we have to figure out, well, we have voltage CN. Where is N to C? N to C will be plotted at 180 degrees from C to N. So here's voltage Cn. So if I add 180, or subtract, but I prefer to add here so we don't have to go past the 0, add 180 to that, so plus 180. It's exactly the opposite vector, 180 degrees from 120. We are at 300 degrees. So there's our two voltages that we need to add. N to B, or sorry, B to N at 240 plus voltage N to C at 300. So let's just pull up the calculator here. So we're going to type this in. I'm still in the correct mode for you, mode 3, second function 8. So let's add our voltages, starting with the first one. So 120 DMS, 240 degrees, plus, next vector, voltage NC, 120 DMS, 300 equals 207.8. So we got the same line voltage, 207.8. So we're adding up 220 volt vectors 60 degrees apart, essentially. And if I want to know what angle it's at, well, we could kind of see it's going to end up right in the middle between the two, right here. It should end up right there because those are the two we're adding. Okay, so let's just have a look at that. Second function, exponent. Look at that, negative 90. Okay, so that's one of the things I want you guys to pay attention to. That it's negative 90. Okay, I'm going to just bring my calculator down for a second here. So I'm going to erase the screen so I can show you why our calculator says negative 90. Okay, so when I get a positive value on our calculator, it will go this way up to 180. But as soon as it goes past 180, it does a negative reference and it goes this way. So I have to go, when it says negative, I have to start from my reference. And I would go back, come on, pen. Go back 90 degrees, and that's where I'd have to plot voltage V, B to C. Okay? So negative 90. So you just have to know that if you see a negative, start from your reference and go backwards 90 degrees. So if we put that in the calculator, if you wanted to figure it out, 360 minus 90, what does that come to? That's 270 degrees. Okay, so that's where I'd have to put voltage BC. All right, so while we're here, what was that rule number 3 for Y? It was that V line leads V phase by 30 degrees. So here's V phase, VB to N. So if I add 30 degrees, that's where I plot voltage BC. So the rule still applies. The line voltage leads phase voltage by 30 degrees. Let's now go and have a look at our last one here, which is voltage C to A. We do not know that one yet. Voltage C to A. Okay, so there's our... So, voltage C to A. Same procedure. I'm at C, and here's my voltmeter. I have to walk the path that my voltmeter sees. So I have to go from C to N, and then I have to go from N to A. So there's our formula. Voltage CA is equal to voltage C to N plus voltage N 2A at their respective angles. Add them up vectorially. Okay, let's go ahead. Let's add this up. So I've got voltage C to N already. I have to determine where voltage N to A is. So I'm just going to write that formula out again off to the side here. Voltage CA equals voltage C to N plus voltage N to A. So I've got voltage C to N. It's 120 volts at 120 degrees plus voltage N to A. Well, where's that? So voltage AN is right here. I need voltage N to A. So it's 180 degrees, or opposite of A to N. So I plot that out, and there it would be. Voltage N to A is 120 volts at 180 degrees. So plus 120 volts at 180 degrees. Bring up our calculator here. Let's put that in the calculator. 120 DMS 120 degrees plus 120 DMS 180, and that is equals 207.8. What angle are we going to be at? Well, it should be leading VC to N by 30 degrees. Let's find out. Second function, exponent. 150. So it tells us exactly where to put it this time, at 150. So let's go ahead and we plot it out at 150 degrees. So note this is a positive 150, right? Because we ended up in the top half. If we ended up in the bottom half, it would give us a negative angle. Let me just get rid of the calculator here. Rule number 3, V line leads V phase by 30 degrees. Okay, so here's line voltage VCA. Here's the phase voltage VCN, and it is leading by 30 degrees. So 120 plus 30 degrees is 150. So line voltage leads phase voltage by 30 degrees. Ahead in time is counterclockwise. So that is all of our voltages. And yeah, so all three phase voltages, A to N, B to N, C to N. So V to N is at 0, B to N is at 240 degrees, C to N is at 120. Line voltages are always 30 degrees ahead, and they're root 3 times square root of 3 higher than the phase voltage, and they're always 30 degrees ahead. And yeah, so 30, 270, and 150 degrees for our line voltage.